So quadratic sequences, that's what we're going to do today. And by the way, I know not everybody online, hold on. Do that for a second. So remember I was talking about my list, about coming up with a list as you're walking through this test. Like I was looking at the test yesterday, and I'm trying to change it because there's that section that I told you to omit yesterday that we didn't get to. I think I'm just going to omit all those problems. They require you to memorize these formulas, and if I give you the formulas, it kind of defeats the point of actually. I mean, anybody can plug numbers in. Like if I said, hey, plug a 7 in, I think everybody's okay if I handed you the formulas. So to me, there's really no point in it. It's certainly not a topic in pre-cal. So for you guys, your list, when you see a problem and I ask you to find the sum or to do something with it, the first thing you have to do is identify what kind of sequence it is, right? Right? I mean, you don't want to be using an arithmetic formula on a geometric sequence or vice versa. And then identifying them, a lot of times you can kind of it's really easy to get lost because there's so many sequences now. And in Algebra 2, it was like arithmetic, geometric, and maybe a harmonic. But there's some other things that we're going to be looking at. So these are the 6. This, I guess, could be construed as 2. But these are the 6 things that could possibly happen to you. And if you have a running list in your head, and you're looking at it, and you're like, dude, I don't know how to find the sum on this thing, because I don't even know what kind of sequence it is. If you know how to identify each of these, you'll be in good shape. And this is the only one we haven't talked about so far. So we're going to talk about this today, and then we're just going to review some stuff and keep plugging along. But the bottom line is you got arithmetics, geometrics, 2 geometrics woven together. Right? Don't confuse that with the fact that every geometric could be thought of as 2 geometrics. But sometimes you have one that's not geometric, but it's just 2. Right? And then the strange sums, we had 2 kind of patterns we were looking for. And by the way, I was checking y'all's stuff off. If I didn't mention this yesterday, a lot of you, the strange sums had the title on 1 page, but it was really a 2-page sheet. And I counted them 3 points apiece. Your homework was worth 6. I gave you credit if you just gave me one of them. But for your sake, a lot of people just turned in the one with the weird patterns on the bottom, but you didn't turn in the part that had the arithmetic over geometric. Make sure you're doing those for your sake. I mean, you'll still see a few more like on a review or whatever, but make sure you understand that process. And then we talked about harmonic yesterday, and then all those other problems you had with the bouncy ball and all that kind of stuff, all those fall under geometrics or the weird patterns. Yes, know those. I might grab a couple out of that sheet and throw them on your test, but understand how to do them. But then today we're going to talk about quadratics. And quadratic sequences used to be one of the harder things that we did because it involved a bunch of math. But over the years, I've had some really clever students notice some interesting patterns. And one guy noticed something really, really great. And it really makes the process of dealing with quadratic equations one of the easier things we do. Now, you still have to learn that process. You'll see that today. But keep this running list in your head. If you have it in your head, write it down. By the time, if you've done the review sheet and you're doing it all well, then it's in there. But if it's not and you're getting stuck, make sure you have all these 6 that you're checking off. All right? All right. All right, so today I want to talk about quadratics. So if you will turn in your book to the quadratic sequence part, we'll get busy on that. Anybody got any questions on anything before I'm going in? Anyone? I don't know why it's taking me this hard to realize, or this long to realize this, but on a PDF document, the way I have my document formatted, this is really cool. I can go right to quadratics and click on it. Bam! Cool.
Very
Never
nice.
knew that.
Very nice.
Anyway, makes it kind of nice. Okay, so there are some patterns on these quadratic sequences, but first I want to talk about what a quadratic sequence is. Y'all know what a quadratic equation is, right? And a quadratic equation is an equation used to solve what kind of expression or equation? A polynomial with a power of 2. So obviously, if there are equations that can be written in like ax squared plus bx plus c form, y equals, well then there are sequences that can be written in that form as well. So think about this as y equals ax squared plus bx plus c, but instead of having x's and y's, I have terms and places. Are you with me? And when you look at one of these, if I were to just start plugging a 1 in to a sequence, it would spit out the first term. I'd plug a 2 in, spits out the second. Plug a 3 in, spits out the third. So the question is, how can you tell by looking at it that it's quadratic? Do you see some pattern right there? It's a really simple thing once you see it. If you're not looking, you can't see it. Anybody? I know somebody sees it.
Arithmetic sequence within the differences of the two.
Okay, so if you were reading, you could see that, but if you're not reading and you look at it, you could go, oh, the common difference here, well, it's not a common difference, it's a difference. The difference between these two is 2. The difference between these two is 4. The difference there is 6, 8, 10. So if the differences between consecutive terms or successive terms is arithmetic in nature, then that means that the actual sequence itself is quadratic. Are y'all seeing that? Now that's an interesting little pattern there. What that means is, so when you look at the differences, 2, 4, 6, 8, 10, it's interesting that the differences are arithmetic, and arithmetic sequences come from linear functions. Well, quadratic sequences, and linear is like mx plus b. Quadratic sequences come from quadratic equations, which are like ax squared plus bx plus c. So you're just moving up a power. And when you move up a power, everything kind of increases by an x, and then a constant. And actually, you could use that same information to identify a cubic sequence. A cubic sequence, when you looked at the differences, the difference would look quadratic. So for instance, I might have another sequence that was like 5, 8, 13, 22, 37. So if I were to give you a sequence like this, which we're not going to actually talk about much, we might have like a bonus or something, Steve. You can look right here. The difference between 5 and 8 is what? 3. And between 8 and 13, 5. And between 13 and 22, 9. And 22 and 37, 15. So if the differences between this were that, and that's quadratic, and I know that because the differences between that are linear, you're just moving up a power again. So this would have been a cubic equation, or a cubic sequence, and it would have come from something like ax cubed plus bx squared plus cx plus d. Are you kind of seeing that? But that's an interesting thing. You would not have been given a sequence like this ever. I mean, I might, again, as just to throw it out there, it's just to kind of test you maybe on a bonus, see if you're with me. But if you look at something like this and you're like, I have no idea, that doesn't fit any of my rules. But if the differences were quadratic and you went, oh wait, I know that's quadratic because the differences, those are linear, then you could actually find, say, the next term by doing what? What's going to be the difference between 37 and the next term? Can you see it? 23. So if the difference is 23, my next term is 60. And the difference between this and the next term would be 33, so my next term would be 93. And you could keep progressing that way. But we're going to focus on quadratic sequences for now. Okay? So these quadratic sequences, that's how you're going to identify what you have. You identify it by looking at the differences. If the differences are any kind of arithmetic sequence, anything, then you know that it's quadratic. Okay? So a lot of times in quadratics, you're asked to find the next 3 terms. So if I said, hey, or the next term or whatever, how would you find the next 3 terms here? What would you have to do to get to the next term? Speak up, it's not even Monday.
And 12.
Add a 12, right? So you'd add a 12, that gets you to 45, and then add a 14, gets you to 59, add a 16, gets you to 75, and that shouldn't be a problem. What's a problem is, how do you get to the 100th term? And I particularly don't really want to find 84 more terms doing this process. Now there are a lot of ways to go about this, but one way I have found, and this used to be a trick I used to show, was to say, well, if I need to get to the 100th term, right, then aren't I really adding 99 of these differences to 3? Because think about it, I'm adding 2 to get to 5, and then I'm adding 2 and 4 to get to 9, and then I'm adding 2, 4, 6 to get to 15, and then 2, 4, 6, 8 to get to 23. So if I want to get to the 100th term, couldn't I take the first term and add 99 of those differences? Are you with me? But technically, what am I doing? The differences are all different. So to add the 99 things I need to do to get to the 100th, what am I really doing here? And I'm going to show you a better way than this, but this is what I used to do. And I thought I was really clever when I did this. What am I doing if I'm adding 99 of these? I'm doing the sum of an arithmetic series, right? Does that make sense? So, say I only want to get to the 10th term, then I would say, well, I need to add 9 halves, first term, 10th term. Are you seeing that? Well, if I want to get to the 100th term, I need to add 99 of these. So I'm going to say 99 halves. The first thing is a 2, and again, I've got to add all of these up all the way through that last 99th term. I'll call it A99. So I'm going to add a 2 plus whatever the 99th term is in this. Not the 99th in this, but the 99th term in my sum. And that's a little annoying. What's the 99th term in 2, 4, 6, 8, all the way whatever? Anybody know? Some of you are you're not thinking. I know what it's like to sit there and go, and you just stare and wait for somebody else to use their brain. It's so much easier. And then you write it down. And you haven't learned. Think. Hurt your brain. How do I find the 99th term in this 2, 4, 6, 8? Because I got to add all these together and then add them to 3. The arithmetic. So I could pull out my arithmetic formula to help me here and say, all right, the 99 terms, not in this, but in that, would be what? The first term, the 2, and I'm going to add it to 99 minus 1 common differences is also 2, right? And what's 98 times 2?
196.
196 plus 2 is 198, and I'll plug a 198 there. My first term right here is a 3, and that would find me the 100th term. Now that is an okay way to find terms like this. But what I found with my students was a way to not just manipulate and find a term, but to come up with a formula for this expression. Because remember, if this is quadratic, then there's some formula out there. And if I can just figure the formula out by finding the A and the B and the C, then I can just say, oh, if I want the 100th term, plug 100 in. If I want the 1000th term, plug 1000 in. To me, that would be easier if it was easy to find A, B, and C. And originally it was not. And this is what we had to do. And I'm going to show you the progression of thought. Over the years, I had one random student, then another random student, and then the third one was awesome. I mean, this guy was super, super smart, and he did something that really made our lives super easy on this, finding this formula. So what I just showed you there, you could still think that way, but it's kind of antiquated now that we have a process. So let me show you what you would do beforehand. And you might remember this from when we played around with matrices or something at some point, but if you don't, just stay with me. So, can I conclude since I've identified this as a quadratic, that there is some equation that fits this. And I don't know what the A, B, and the C are, but there's some equation out there that would have this form. Would you agree? And would you agree that that right there is the term, the Tn, which is like a y, in the first place? And that the 5 is the term, the Ty, or the Tn, which is like the y, in the second place, because the place is like the x. And would you agree that the 9 is the term in the third place? Now, if that's true, then technically, I can plug this NTN, NTN, NTN in for N and T and make 3 separate equations. Now, technically, I can make a zillion equations because I have all these terms. But if I have 3 variables that I need to solve, it makes sense that I would only need 3 equations to solve for those 3 variables. Does that part make sense? Yes? Because if it doesn't, then you're going to get behind and it's just you're going to be hearing like the Charlie Brown parent. That's all you're going to hear from here on out. All right, so I'm taking these points, and I always use the first 3, and I'm going to show you why I always use the first 3. You could use any of them, but the first 3 are going to have a neat little pattern here. So the first 3, if I do that, 1, 2, 3 is my N. In this case, 3, 5, 9 are my TNs. I'm going to plug those in right here into that formula, and here's what happens. Check it out. I'm going to plug 1 in for N, 2 in for N, and 3 in for N, and then I'm going to take the Tn and plug the terms. And if you're wondering why I put the Tn on the right side, I think it's because you guys are more used to solving with the equals on the, and then the stuff on the right. But I didn't have to do that. I could have said 3 equals that, 5 equals that, 9 equals. Are y'all with me so far? Now, what I told my kids 20 years ago was solve the system. And they were like, oh man, seriously, solve the system? And it was a pain. But y'all remember doing that in Algebra 2? Where you'd like group these 2 together and say, try to eliminate A through like elimination method. And then maybe you group these 2 together and try to eliminate A through the elimination method. And then you would come up with two new equations with B and C. And then you would solve for B and C and then plug them back in here and get your A. You can always do that. It's just kind of a pain. So one year, Mark Catlin, I don't know if y'all know Mark Catlin. I mean, he's old now. He's like 37 or something. But Mark, he was a youth pastor around here for a while, and then he went up to Princeton. He did some RUF up at Princeton or something like that. But I remember Mark rolled in here one day, and he was always looking for tricks to kind of eliminate the pain and suffering of doing the math. He said, Mr. Hurry, I noticed something. All right, we call this Catlin's rule. He goes, I noticed something. He goes, if you always use 1, 2, and 3, the first, second, and the third terms, then this part on the left is always the same. Which makes sense, right? Because it's a formula. Remember, an squared plus bn plus c. So if I plug 1s, 2s, 3s, the left part's always the same. The only part that's not the same are what the actual terms were. Does that make sense? Yes or no? Because remember, I'm plugging into this formula. So if n is always going to be 1, 2, and 3, because I'm using the first, second, and third terms, sorry, I'm putting the t in over here. If n is always going to be 1, 2, 3, then it stands to reason that the left side's always going to look like that, that, and that. And he said, if that's true, then look what happens if I multiply through the middle part by a -2. If I multiply the middle part by a -2 and add everything together, I get 9a and 1a is 10a minus 8a is 2a, but look what happens to the b's. Cancel. Cancel. And then you have to come over here and add those 2 values. That right there is this -2 times that. But you add this together and you get this. And you find your a value real quickly. And back then we were like, oh, that's huge. Because if I can find my a value, then I could just come back here and ignore this. I could come back here and plug a 1 in, and a 1 in, and a 1 in, move those constants over, and solve for B and C pretty quickly. So we thought that was great. But the great part about it is he said, well, I've noticed, Mr. Hurry, all you really end up having to do to find A then is use this formula. 2a equals the first term minus twice the second plus the third. Because if you think about it, first term, third term, minus 2 times that, minus twice the second. So really, he would come in here and just go, all right, every time, he would not even write all this. He would say 2a equals 3 plus 9 minus twice that, so 18 minus a 10, 12 minus a 10, and he would get that and he would solve for a. Once he had his a, he would plug his a in. He really didn't even need to do it in 2 equations. In 3 equations. He would just plug it back into the 2 equations like this, subtract 1, subtract 4, and he would get b plus c equals 2, 2b plus c equals 1. He'd solve for b and c, and he'd have his formula. And we thought, oh, Mark, you've saved the day. And then, are you kind of tracking with me? So right here, for an example, he would use this formula to get a. He'd plug a 1 in there. He'd solve for b, he'd solve for c, and then he'd plug the 1 and the b and the c in there, and there's his formula. And now when I say what's the 100th term, you just plug 100 in. What's the 50th term? Plug a 50 in. And we thought that was great, and honestly, not bad. But there's even more fun to have it. All right, then along came a girl named Aubrey Wallace. And Aubrey struggled at times. She was not super motivated. Actually did real well in AP Calculus. When it was something she had to get, she wasn't real big on memorizing and stuff like that. But she started noticing some patterns. She started noticing that when you originally identified the quadratic, remember how you go 5 minus 3, 9 minus 5, 15 minus 9? She noticed when I was finding that 2, 4, 6, 8, which was the difference between these. You with me? 2, 4, 6, 8, 10. What's the common difference of the arithmetic part? 2. She noticed that what I got up here for for the sum of these was always that common difference. Are you with me? She just noticed that on every quadratic where the difference between the terms was arithmetic, and that's the check, right? The common difference of those terms happened to always be what you got by taking the T1 and the T3 minus twice the T2. So that made it huge. Now my formula became even easier. I didn't even have to figure these 3 numbers out based on this. I no longer had to go T1 minus 2T2 plus T3. I just looked at the common difference of the differences between the terms, threw it in there, and solved. So, if you have an expression like this, 5, 8, 13, let me make something different. 5, 8, 14, 23, 35. And you looked at this and you went 3, 6, 9, 12. Oh, look, since that's arithmetic, I know this is quadratic, right? So no longer did he need to go, oh, well, the A value I can find by going TA equals first term minus twice the second plus the third. I don't have to go 29 minus 16, which is, 19 minus 16, which is, I don't have to do that. I can just say the common difference of this was plus 3, stick it right there and set it equal to 2a. Which was a huge trick, because now I didn't have to memorize that part. This junk right here. I could just look at my differences and go, common difference is 3, 2a equals 3, a is 3 halves. And I have my a term, I go back and I plug in my a term, and I solve for b and c. So that was huge. Now you still have to memorize that little trick there, but it really made life easy. And then, the money maker, Dmitry Gavrikov. We called him the Big Russian. And he was kind of a big Russian. Played soccer, but he was like 6'1", 185, 190 pounds, really fast, and torment on the soccer field until he got like 4 concussions, and then he He missed a whole semester of school, couldn't play soccer anymore, but he was a genius. But Dimitri noticed this, and it was pretty impressive, I thought. Dimitri said, okay, let's just say, for example, that I had a quadratic like 2, 7, 18, 35, 58, 87. And I know it's a quadratic again because 2, 7 is 5, 7, 11 is 18, 17, 23, 29, right? So as far as finding my A term, I would say 2A is what? Common difference is 6 right there. So I would say 6, and I would have my 3. Now we already know that from a combination of Catlin and Wallace's rule. But then he said this, Mr. Hurd, what if we were to find the term before that? And I'm like, well, there is no term before that. He goes, yeah, there is. I mean, it's a sequence, right? Let's think of, not T2. What if I thought about that as T0, or basically the 0 place? I'm like, huh. He goes, well, what would be that term? Think about it. Based on this pattern, what would I have added to this to get 2? It looks to me like I'm doing what each time? 6, 6, 6. So what do I add 6 to get 5? -1. Which means what would this term have been to get me 2? 3. Now if you're looking at that right now and going, how can a sequence go down and then up? It's quadratic, right? Quadratics can go down and then back up. Linears can't, right? But quadratics can. Now do they all? No, because sometimes I start to the right of the vertex, kind of, and it just goes up, right? But sometimes I start to the left and it goes down and up. Well, what does that mean? That means my 0 term was 3, or the n is 0. Now, if you think about that, check this out. Oh, we find a blank space. What does that tell us about that? When n is 0, the TO is 3. When n is 0, the TN is 3. What does that tell you? C is 3, which means if TN is 3, and when I plug in a 0, TN is C, then what does that tell you about C and TO? They're the same thing. So what that means is if I can find that term right to the left of where I started, if I can find that, that not only is my 0 term, but it's also my C value. And guys, if I can get the A and the B value that quickly, I can just throw the A and the B value in there. I'm sorry, the A and the C value that quickly. I can just throw A and C in my original formula and solve for B effortlessly. Are y'all seeing that? Let me show you another. So right here, say the sequence was 5, 9, 15, 23, 33, 45, right? So my differences are 4, 6, 8, 10, 12. So if that's the case, what would the term right before that have been? What would I have added to it to get to 5? Based on this pattern. 2. And what would that number be that I add positive 2 to it to get me 5? 3. So that not only is the T0, but it's also the C term. Now you have C. And how easy is it to find A? 2A is always what? The common difference of these. And what's the common difference of those? 2. So now my A is 1. So now I got A1, I got A is 1 and C is 3. Now remember my formula. My formula said AN squared plus BN plus C is a term. I can use any term now that I want, but what would be the easiest term to deal with? What's the first term in this sequence? T1 is 5, so when n is 1, the term is 5. So when n is 1, the term is 5. Plug in your A and your C, and you'll find your B. Plug in your A, plug in your C, and your B is also 1. So now I know my A, my B, my C, and I know my formula. So my formula is A is 1n squared, plus 1n plus 2. And now if I want to find we started with this, right? 1, 2, 3, 4, 5, 6. We'll just check it. The sixth term, T6 equals 6 squared plus 6 plus 2, 36 plus 8, 44. Oh. Plus what?
C.
Oh, C is 3, sorry. What happened? The rule is blowing up. So if I wanted to find the 100th term, I'd have a formula. Now I've talked a bunch, and it sounds almost like through my explanation that the very first way I showed you might have been easier, but it's really not. So let's just do a couple more of these just to play around and see. Make sure you're with me. All right, so find the formula for the nth term of the following sequence. So I got this sequence right here, and I want a formula. So real quickly, I look at this. I don't even know that it's quadratic technically yet, so let's check. 4, 7, 10, 13, 16, 19. And sure enough, I look at this, and I see plus 3, plus 3, plus 3, plus 3, plus 3. So my common difference of the differences is 3. So how do I quickly find A? What's my trick for quickly finding A? 2A equals that. So 2A equals 3, A is 3 halves. I've got my first A value. I got my A value. Now, how do I quickly find C? C is that term that came before that. Well, based on this pattern, what do I add to that blank to get 9? Do y'all see that it's 1? Because if you decrease this by 3 going this way, that would be a 1. So what do I add? What number when I add 1 gives me a 9? 8. So 8 not only is my T0, but it's also my what? C term. So now I have C is 8. And to find B, I'm just going to go back and take my A plus B plus C equals T1 expression. And why am I going to use that one always? Because it's easy. I could use any of them, but again, I'm basically taking AN squared plus BN plus C equals TN, but I'm just using the first term. And the first term will always be A1 squared, B1 plus C, so it'll always be A plus B plus C equals the first term. So I go in there and I plug the A that I know, the C that I just found, the B that I don't know. The first term is a 9, and I subtract 8 and get 1. I subtract 1.5 and get -1/2. And now I know my A, B, C, and I plug the A and the B and the C in there in my formula. And now from there I can find anything I want. Y'all with me? So help me out. Do I even know this is quadratic? Let's see. 7, 10, 13, 16. Okay, arithmetic, it is quadratic. And what's my common difference here? 3. So what's A? 2A equals 3, A is 3 halves. It's that quick. Thank you, Mark and Audrey. Now, how do I find C? What would I add to the blank to get 12? 4. What does that make the blank? 8. So that tells me C is 8. Once I get that, how do I find the B term? A plus B plus C equals what? 12, the first term. I plug in the A. I don't know the B. I plug in the C. I subtract that and get 4. Subtract 1.5 and get 5 halves. right? I got my ABC. Find the formula. The formula for the nth term is A, 3 halves, place squared, n squared, plus B, 5 halves, n, plus C. And if you don't believe me, let's check. Shouldn't the 5th term be 58 here? So T of 5, if I plug that in there, it gives me 3 halves, 5 squared, plus 5 halves, 5, plus 8, 75, plus 25 halves is 100 halves, which is 50. 50 plus 8 is 58. So it checks out. And then if you jump down to number 5, find the 100th term. So this time, it didn't ask me for the equation, just the term. And usually on a math team test, this is probably what they'll ask, is if they ask you for the equation, you could just look at the multiple choice answers and see which one actually works. You can just plug in certain things and see if you're getting the right terms. So they normally ask you stuff like this. So technically, you could use that initial method if you wanted to. I don't encourage you though, because you could have the equation and then use the equation. So I'm going to find the equation. First, I got to check to see what it is. 1, 3, 5, 7, 9, 11. So sure enough, that's arithmetic, and the common difference of that is 2. So what does that tell me about my A value? 2A is that common difference. A is 1. Sweet. Now what do? Find the 0 term. What did I do to find the 0 term? This is a little tricky on these. What did I add to the blank to get a 1? If I decrease this by 2, that's a -1. So what would that number be that when you subtract a 1, it gives me a 1? 2. And you can see it go down and up again. But again, it's quadratic. That makes sense that it can do that. Right? So what does that 2 stand for? C. And then how are you going to find your B term? Remember, your formula says an squared. You don't have to write this. Bn plus c is tn. You can use any term in any place, but if you use the first term, then you plug a 1 in there. It's just always a plus b plus c is first term. So plug in your a, don't know b, plug in your c, and you get b is -2. And now that you have your a and your b and your c, you have your formula. And once you have your formula, you can find the 100th term. So 100 squared, 2 times 100 plus 2 gives you 1, 0, 0, 0, 0, minus plus 2, minus 200. So what is that? 9802, I think. Not too bad. So if you look at your assignment sheet, tonight says to finish the quadratic stuff on this thing, and then there are 3 problems on your homework sheet. On your assignment sheet that are listed. So do the problems on this that go through 6 that I didn't do. I think there's 4. And then you also have 7, 8, 9. And if you want to try to squeeze 7, 8, 9 across the bottom there, you might be able to do them. Or just attach a sheet of paper to it. No big deal. Not quite sure why I didn't just put 7, 8, 9 on here. A task for another day, I suppose. Y'all tracking with me? All right, and then tomorrow, guys, if you've looked ahead, we're going to finish that out by tomorrow. We're just going to work on those Grissom high school problems, which are next. We're just going to take a day working on those, and some of them are hard, some of them are not, but it's just a random bag of tricks there. And then on Monday, we're going to do binomial expansion again, like finding the 5th term, finding the middle term, and I'm going to increase the ante a little bit, start throwing you some wild card little curveballs or whatever. And then we're going to review Tuesday, test Wednesday.
Did you give this back to us?
And by the way, that's not going to be next week, that's gonna be in 2 weeks. Dude, I don't know. I gave you a bunch back today. Check it out. If it's a zero, throw it back in. All right. Good day. Yeah.